you can describe the state of a particle on a real line in the phase space by a phase space function, which is a function of q and p, and this is a genuine probability distribution on phase space. So, in this picture, the pure state, or just q and p taking values q naught, p naught, describing a pure state of a particle would then correspond to a delta function. This will be our phase space function. But more generally, and we can then speak of, in analogy with quantum mechanics, we can speak of mixed states in classical mechanics, where this phase space function is not a delta function, but a more general probability distribution. All right. Now, certain notions which are of phase space, which we would perhaps come across later, are the following. You have, first of all, you can consider the lines through the origin in the phase space. All set of lines are referred to as isotropic lines. These are not going to be of great importance to our present setup, but since we are talking about phase space, I thought I will mention them to you, so that later on when you come across them, you are not at a loss to understand. Or also isotropic lines. What are the there is another, on the phase space, there is another notion which is available, which is called a symplectic product. And that is defined in the following way. Suppose I have a point sigma on the phase space, sigma prime, where sigma stands for a point in the phase space QP, sigma prime stands for Q prime P prime, then sigma sigma prime is defined as P Q prime minus Q P prime. So, with any 2 points in the phase space, you can define a symplectic product, which is given by, this is the definition of the symplectic product. The isotropic lines, or the set of points, the lines going through the origin, can then be characterized by, so a line would then be a set of points sigma and sigma prime, such that the scalar, the symplectic product of sigma sigma prime is 0. You can see that if I set this equal to 0 in the QP plane, this gives a linear relation. Please stop me at any point if you have any query or question, or if there is something which I have not stated clearly. So, you can see that if you set this equal to 0 in the QP plane, this describes a straight line through the origin with the slope p prime by q prime, and therefore describes an isotropic line. So, sigma, a line in the phase space is a set of points sigma and sigma prime, such that the symplectic product of any two is equal to 0. Now, once we have a notion of a symplectic product, we would also like yes?
Why it is called isotropic?
Eh?
Why it is called isotropic?
Isotropic line, the word has its origin in the context of what are called Lagrangian submanifolds, but we will right now you just take it as a name, isotropic line. First of all, there is no constant, it is a line going through the origin, but right now just take it as a terminology. Yes?
The product is taken on the same line, sigma and sigma prime.
No, sigma and sigma prime, I give you 2 points. Please I'm very happy that people are asking questions. It will help me a great deal to, if you ask questions then and there rather than wait till the tutorial. Suppose I give you sigma and sigma prime, 2 points, I take 2 points. Then these 2 points define a line through the origin. Is that clear? Because if I took sigma 2 points QP and PQ prime, set it equal to 0. In the PQ plane, this describes, if you think of Q and P as the coordinates, this is a line through the origin, right? Y equal to mx type of an equation. So it's a line through the origin. So if you, so what I'm saying is that the line through the origin is completely specified by giving 2 points on the line, all right, in this case. I'm defining it this way.
While defining space, there is you use manifold and tangent space. Just for the sake of understanding, what is the formal definitions of these?
For the formal definitions,
Manifold and tangent.
please, it's beyond, not a part of this. This is, we can discuss it separately, but there are excellent books. If you like, I can give you references to them where you can find that details to. As I said, I'm not going to talk about classical mechanics in any great detail, and any such questions may be addressed outside the lectures, and I may also not be able to answer questions at the level that you are asking. I'm just trying to give you a rough idea of flavor of what these things mean and why are they important. Yes? Eh? Huh? Which lines? No, now look, the use of all that was just to indicate that given generalized coordinates, which are points which label your manifold Q. Again, there are many questions in that manifold, whether you can give assign coordinates globally or not. I'm not going to go into that. So suppose a set of coordinates are given, we describe the manifold, then to that you can associate a phase space, and that's where there is a construction available. Now details you would have to worry about it. Now we have got a phase space, for example, for a particle on a real line. Then we say that Q describes the position and P is the momentum. Q and P by that construction take values from minus infinity to plus infinity. We put it together in the form of a plane. Now again, there is no notion of these things being perpendicular. If you wanted, you could have drawn lines like this with Q here and P here. But this is just a picture visualization of the phase space, all right. There is no meaning to this coordinate being orthogonal to the momentum, nothing of that kind. Now on this phase space, yes.
Give me the definition of that line also. Explain the definition of that line, symplectic line.
Huh?
Could you please repeat that?
What I am saying is that if I consider a line through the, you're given 2 points sigma and sigma prime, then the set of all points such that this scalar product is equal to 0, the symplectic product is equal to 0, we call that a line, all right.
If you are given 2 points, it always says
No, that depends on what kind of objects Q and P are. If you are, whether you are dealing with, I'm sort of anticipating generalizations later on, which I would not discuss when Q is a finite field or P is a finite field. So in this, at the moment, you have got a line through the origin is basically Q is equal to M P or P is equal to M Q, where M is the slope of that line. That's all I'm saying. Is that clear?
Sir, so,
And this relation,
sir,
suppose, yes,
so these lines should be the lines through the origin,
through,
not any two points.
eh?
I mean, these lines
Yes.
should be the lines through the origin, not any two points.
Yeah, they will go through the origin because, see, the origin scale, symplectic product of origin with every other point is actually is 0, right? All right, so you can take this origin as one, this is always 0. Now you take 2 points and this set the symplectic product equal to 0, then you get a relation Q is proportional to P, which is the definition of a line.
Equating the flow,
M would be the P prime by Q prime. Yeah, that's all that is. Okay. Now, once we have this notion of a symplectic product and lines through the origin, you can ignore the word isotropic if you don't like it. There are two things which come along with it, namely, so I take some line through the origin. This line gives rise to a set of lines parallel to it. A continuous family of lines parallel to it. This we would call a foliation of the phase space. Now, please, if you don't like or just treat it as a decomposition of the entire phase space in terms of a set of lines parallel to a given line. All right. How many such decompositions are possible? Infinitely many. All right. Now, the reason why I am talking about this is because each decomposition allows you to find, starting from the phase space distribution function phi qp, it allows you to define a set of probabilities which are called marginal distributions. That is the idea behind introducing this decomposition of the phase space in terms of a set of lines. So, we have infinitely many. One possible decomposition could be this. And if I take the phase space function qp and integrate over q, for example, integrate over p, let's say integrate over q. So, what I would end up with is some function of p alone, and because this is a probability distribution, its marginal distribution will also be a probability distribution. This is given from the fact that FQP is a probability distribution. Of course, I could have chosen. So, here what we are doing is in the language in which I have introduced so far, we are taking FQP, decomposing the phase space into this set of lines, integrating over all q. So, there are P naught prime and so on. For each value of P, I have a line, I integrate over Q, and what I get is a probability distribution in the momentum space in this example. Similarly, you could have considered this decomposition. Of course, the line through the origin is our representative that defines a set of lines which decompose the phase space in terms of non-overlapping into disjoint subsets, and each of them then defines a corresponding marginal distribution. You could have taken this, yes.
So this F is an any arbitrary line by a function?
FQP is a probability
Is
distribution.
a probability.
Right.
So they can be any arbitrary line classification.
You can do it, yeah, you can speak of a marginal distribution associated with this decomposition, marginal distribution associated with this, marginal distribution associated with this. So starting from the phase space description, you take the marginal distributions of various kinds, each associated with one particular decomposition of the phase space, and you get a probability distribution. All right? So these are called the marginal distributions. Yes.
Can this be looked at this way? That if I fix a sigma,
Yes.
if you are taking the symplectic inner product
Yes.
equal to 0, that is the line passing through the origin.
Yes. Yes.
Now we fix another sigma
Yes.
and we take the symplectic product which is equal to some k.
Yes.
So these are basically the equivalence classes.
That's correct. But sigma prime equal to k will not describe a line parallel to this. That you have to keep in mind.
But basically,
Equal to 0 is yes. It describes a line through the origin. But it does not sigma prime equal to k does not. So in some sense the language what you have done is correct. You have started with to couch it in your language, we have got the phase, we have got a plane, and we decompose it. Each line through the origin is a representative of the set of lines parallel to it, and therefore defines a decomposition of the phase space. Given any such decomposition, we can, given the phase space distribution, you can describe the corresponding marginal distribution by integrating along those lines. That is all I am trying to say. Nothing very fancy or very great, but it's just something which we would like, because just to anticipate the discussion later on in the quantum case, where you would have a phase space description, what you would like it to be analogous to have the properties which the classical phase space distribution had, and you would like also to have it for the phase space distribution to have this marginals property. And we would like to see to what extent we succeed in constructing such phase space functions. Yes?
So the marginal will be unique regardless of which decomposition I am taking.
Marginal would be unique means?
For instance, I have an FQP and I am taking one particular decomposition and then I am doing the integration.
Yes, yes. You will get a probability distribution over, yes.
Yeah, but that will be the same regardless of which decomposition.
No, 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 no. That will vary. That will vary from, for example, here you did this integral, you got some probability p marginal distribution in terms of momentum. Suppose you integrated over p, you will get a different function.
For the same variable.
I don't understand the question.
For different valuations,
Yes?
then you get different marginal.
Of course, the functions will be different. Probabilities will be different.
I'm not talking about the probability function, I'm talking about the family of lines that
Yeah, take a family of lines and you do this integral along these lines, you will get some function of p. If you change the set of lines, you will get a different function of p. I mean, that's all right. Sorry? Fourier transformation.
So I'm saying if f is a constant of 20
Yes,
and this is the way we are taking the marginal,
yes.
and now I'm considering a different foliation,
Different foliation, yes.
then it would mean that the q has changed to some q prime.
Yes, yes,
It has to be written in that
yes, yes.
coordinate, and then you integrate it.
That's correct. That's correct. And that is exactly how this is. This I am spending so much time on it because Q and P are what are Q and P in classical mechanics? The generalized coordinates and momenta are defined and they obey the classical Poisson bracket relations. This is equal to 1. where this symbol denotes Poisson bracket, and I hope everyone knows what a Poisson bracket is. Everyone knows what is a Poisson bracket? Eh? Anyone? So let me just write it down for completeness. So if I have two functions of phase space f, g, then the Poisson bracket so this is the notion of a Poisson bracket. And in Hamiltonian mechanics, the fundamental Poisson bracket between the position, coordinates and momenta obeys the relation that QP is equal to 1. All right. Now you can ask, just to answer, connect it with the question that you asked, you can ask, what about canonical transformations on Q and P? Suppose I do linear canonical transformations. So I start with Q and P, and I consider Q prime and P prime some linear combination of Q and P. And actually the reason why I am doing all this is just to suppose I consider some linear combination of Q and P, and then I can find out what are the conditions on A, B and C, D that must be satisfied in order that Q prime P prime also obey the same commutation relation. So they are, you know, there is nothing special about Q and P. So our phase space, we would like that the phase space or the quantities of physical interest must, we will see later on, must have this covariance under these linear canonical transformations. That is the reason why one is introducing all this. Eh? We will come at this stage. You just keep in mind that there is nothing special about Q and P. You could have taken linear canonical transformations and you could have got Q prime and P prime, which are just as good a description of the phase space as the original Q and P. So any quantity which has some physical significance should not depend on how you parameterize your phase space in terms of Q or P or in terms of Q prime and P prime. That is the idea, and that is an important concept which will run through as we go along. And in answer to your question, these transformations then, and the reason why I define this machinery is the following, that under a linear canonical transformation of this kind, the isotropic line or the line through the origin goes to another line through the origin. So you have, is that clear? You can see that in a minute, that first of all, let us spend some time on these linear canonical transformations. So we've got, you can see Q prime is equal to AQ plus BP, or we can write it as in a matrix form. Q prime P prime is equal to ABCD QP, and you can check that in order that Q prime P prime obey the same, satisfy the canonical commutational relations, this matrix ABCD, of course ABCD are real numbers because we are dealing with a real phase space, such that AD minus BC should be equal to 1. All right? AD minus BC should be equal to 1. So at the moment we are dealing with the canonical transformations are implemented by matrices, real matrices in this present context in 2 dimensions, which have a determinant equal to 1. SL2R. Later on, we will see that we will define a more general group of canonical transformations, and I'll leave the discussion till later, which is called SP2NR. And we are dealing with the situation n equal to 1, in which case it happens to coincide with SL2R. But for larger values of n, SL2R, you don't SP4R, or when you are dealing with phase space where n describing two state quantums, two Cartesian degrees of freedom, the group of canonical transformations will be this, and SP4R will not be the same as SL4R. They will be different. At this level, in the context of 1 degree of freedom, they are the same. Now, what is the connection? Let's just formalize things a bit, and then I will. Is that what clock accurate, or is it fast? Is correct. All right. Now, you can see that the action of this canonical transformations on the phase space, so Q prime, P prime, you can see that if you have QP, 2 points, sigma and sigma prime, let me that this QP, Q prime, P prime such a transformation will take an isotropic line, a line through the origin, to another isotropic line. So, this will, now mind my words, it takes a line to a line. I am not talking about it takes a point. You would think that this entire operation on phase space is rotation. No, more than that, because it takes a line to a line. The point may not, of course, under rotation, the point will go to another line, but there may also be other operations like scaling involved. So, this group has both aspects built into it, rotations and scaling of Q and P, and that one has to. Of course, it contains, the group contains usual rotations, but it has rotations and scaling both in it. Is that clear? So, the statement is that it takes a line to a line. That is to say, all points on this line under this change of variables will go to another line, and not necessarily a rotation, it could be also involve scaling. Okay? So, this is the effect of linear canonical transformations on the phase space. Any questions at this level? All right. So, now what we have learnt is, and you can also see that if sigma and sigma prime are 2 points, then under the canonical transformations, the symplectic product remains unchanged. Symplectic product remains unchanged, and in the next lecture I will try and say it in more detail. Just to bring this first lecture to some satisfactory conclusion. So, let me summarize what we have learned. We have learned that we have a phase space in classical mechanics. This is already automatic construction which leads to a phase space. On the phase space, we can introduce a phase space function. The phase space function allows us, depending on how you decompose the phase space, allows you to construct various marginal distributions. That is, you integrate Q or P or integrate them along a set of parallel lines in the phase space. Each such procedure would give you a genuine probability distribution. This property of the classical phase space distributions hereafter I will refer to as marginals property. So now next step is just to indicate what is to come in the later lectures. What we would like is, first of all, how do you describe what does it entail to in constructing quantum phase space description. Once you have such a description in terms of Q and P, then what is the analog of this classical phase space distribution? Does the quantum phase space distribution have the properties of a classical phase space distribution, namely point-wise positivity, that is FQP is a probability distribution. So, FQP is a genuine probability distribution. Then its marginals are also probability distributions. We would like to see whether in the quantum case where state is defined through a density operator, whether I can associate with it in some way a phase space distribution which has these properties. To what extent we succeed, to what extent we fail will be discussed in the next lecture. I will stop here if there are any questions.
This space is a vector space. In general, in vector space, the notion of inner product, it gives geometrically the generalization of angle between two. Does the symplectic product, does it have some geometrical meaning of
Yes, it does. The symplectic product does have a meaning. And it's remember that you have to distinguish it. This is not an inner product. This is not an inner. It's antisymmetric in Q prime and Q. There are things I think connected with it. I will discuss it with you later.
this you have up to now discussed in Cartesian coordinates?
Yes.
Same idea can we discuss in other coordinate systems?
In other coordinate systems, that depends on, I would not like to say anything on this. Say for example, if you had, I have had similar questions, but I don't know the answer. Say for example, in the case of a cylinder. Of course, there are two obvious foliations available, set of lines here and circles here. All right. Now, whether one can consider decomposition in terms of helices on this, I have been looking at that question. I mean, certainly it should be possible, but perhaps the notions should, to the extent possible, carry over in other contexts, but I cannot give any guarantee because I do not know the answer.
Something to do with non-linear.
Eh?
Non-linear canal.
I don't know what this would mean, decomposing it in terms of this helices, because once you have straight lines, you have circles, something in between. I have looked at that question in the quantum context to some extent, but I will not say anything this way or that way at this stage.
Under canonical terms,
Eh? What's the time now?
11 o'clock.
What's the time now? Half an hour. Oh, I see. Maybe I. Yeah, please.
So under canonical transformation, will the symplectic product remain invariant?
Yes.
It will remain.
Yes. The symplectic product, it leaves. That is important of this SP, the action of the SP group is a symplectic product. It leaves the symplectic product unchanged.
Is rotation and this scaling.
Rotation and scaling in a rough way. I mean, one has to read Simon's and Mukunda's papers in order to understand the full geometry and content and various kinds of decompositions. But my aim is very limited. I want you to understand in the context of one variable quantum mechanics, 1 degree of Cartesian degree of freedom, all the things that we can ask and answer, and then some of those, basically some of these very simple ideas which had a very simple and humble beginning, but posed by in collective works of collaborative works of Simon, Mukunda and others, very simple questions, but they had profound consequences later on. So, my purpose here is to simply communicate that to you in these lectures. Now, you said I have another half an hour. 1.5 hours, yes, yes. All right, all right. Let me drink some water. If you have some questions, some more questions, and then maybe there is something which I have not been able to bring out with as much clarity as I should have, or if you have any further clarifications, questions on what I have done so far, please ask me.
You and the participants must know that in the evening you will have 1.5 hours tutorial.
Yeah, yeah. Now, Simon, my aim is essentially what I want to do before your lecture tomorrow. We have one lecture today. Before your lecture tomorrow, I want to bring it up to Gaussian states and statements about that. After that, the fourth one, we can then calculate Wigner functions for various states and how to transcribe master equations in terms of Fokker-Planck equations. Those kinds of things we will, more technical details we'll focus on in that tutorial. So, I think then it will be better, it connects up with, of course, there may be some repetition, but repetition would not do any harm. All right, so let us now proceed. Is there a matter duster which does these dusters? Because these are so. Chandru, I think it's better to have a cloth. All right. Now, we pass on to quantum phase space descriptions. Well, this should be called passage to quantum mechanics. And as you all know that historically quantization meant quantization of a system of this kind that we are dealing with, single Cartesian degrees of freedom, meant that Q and P go to operators Q hat and P hat, where Q hat and P hat obey similar to classical Poisson bracket, they obey commutators relation Q hat, fundamental commutation relations, Q hat P hat is equal to IH cross. This is one way to look at quantization of the system that we are dealing with. So far Q and P were numbers, C numbers, classical numbers. When we go to quantum mechanics, passage to quantum mechanics is given by replacing Q and P by Q hat and P hat, where Q hat, P hat are operators on a Hilbert space H, obeying these fundamental commutation relations. This is one way to look at quantization of the system that we are dealing with. Now, a natural question is, okay, passage from classical phase space variables Q and P. For Q and P, we have this rule, Q and P go to operators on Hilbert space. What happens to things like QP? What do they go to? What do I write for this? Q hat, P hat, P hat, Q hat? What combination do I write? Clearly, this has to be specified by a prescription. You have to say what is the, how do you pass from classical phase space variables to corresponding operators? Because here Q and P at the classical level are numbers which you can write the way you like. They are commutative numbers. You can write QP is the same as PQ, but not so at the quantum level, because Q hat and P hat, the corresponding operators, do not commute. So you have to give some prescription which allows you to write any phase space, any function of Q and P in terms of the corresponding operators, and that is what we would discuss now, and that is what we would lead to a variety of phase space descriptions, because they would, each of them would depend on what prescription you adopt in order to make this transition from a phase space function to a corresponding operators on the Hilbert space. Any question at this stage? So at the quantum level, you have no way in which, at the quantum level, the quantum description proceeds through specification of a density operator on a Hilbert space, which defines a state of the Hilbert space. There is no natural way in which you can associate a phase space function with an operator on the Hilbert space. And what we are going to do is various possibilities that exist and have been discussed in the literature in order to associate some kind of a phase space function of of C number variables Q and P with a density operator, and this is what we are after. Is that clear? So first we have to answer this question, Q and P, Q hat, P hat go to Q and P go to this. What happens to QP? What happens to QM, Pn, and in general, given some function of Q and P, what does it go to in terms of an operator on the Hilbert space? So that is we focus on that first. Before going to that, there are certain preparation which I have to do, and it also allows me to introduce some notation which is standard in almost all textbooks, but it is good if I introduce it now. So what we would do now is quickly go through some technical details of operators connected with Q hat, P hat, and functions of Q hat, P hat. What are their properties? So Q hat is an operator. I mean, we will denote the Hilbert space by H, and its eigenstates are labeled by a number q. Q takes on values from minus infinity to plus infinity. And for q, if you take two coordinate eigenstates, then their inner product is a Dirac delta function. These also give you a resolution of the identity. Whatever I have written down, is there anyone who is not familiar with this notation or what is written here? Is there anyone? I assume that everyone knows this much quantum mechanics. Then, of course, we have the momentum operator, and its, I should ideally use a different notation, but I will continue to use this ket here. And these are eigenstates of the momentum operator labeled by a number which we call the momentum, taking values minus infinity to plus infinity. And they also, like the coordinate eigenstates, also p minus p prime, and they give you a resolution of the identity. These two properties then allow you to write any element of the Hilbert space, any vector in the Hilbert space, in terms of the superposition of the coordinate eigenstates, and this psi of q is the coordinate representation of the vector psi. In this is what it denotes, and this allows you to express uniquely any, associate with any vector psi what we call a coordinate wave function. Similarly, for any psi, you can do a similar thing and associate with it a momentum wave function, by which is a coefficient that appears when you expand psi in terms of momentum eigenstates, and this is defined by this quantity. And as you know, the coordinate and the momentum representations, or the coordinate eigenstates and the momentum eigenstates, are related to each other by a Fourier transformation. All right? So, for example, the momentum eigenstates, when expanded in terms of coordinate eigenstates, because so this is the relation between the momentum and the coordinate eigenstates. Okay. Any questions up to this point? Some of you may not be from physics background, may have some problems with the notation and all that, some clarity on that? Yes.
You wanted to use this curly ket for
Yes, yes. The reason was the following, you know, this Q and P is a label. Now we have, if you understand that I use the label Q for coordinate. If I just gave you this, you could say it's a coordinate eigenstate with a coordinate taking value P. You know, there is nothing to indicate that. So it's sometimes convenient to use this to indicate that you are now dealing with momentum eigenstates, and this is an eigenstate of the momentum operator with eigenvalue p. just to make a distinction, but often nobody makes such a distinction, and from the context it is clear whether when you write P, whether it means a momentum eigenstate or a coordinate eigenstate. You will never confuse it with a coordinate eigenstate where the coordinate has a value P. So that's the reason. Anything?
This line could you please
Eh?
explain? Psi is equal to integral dq.
Here?
Top line.
Yes.
What do you mean there?
So we have, it's good, I'm happy that, so what we want to do is this psi, and Q is a basis in the Hilbert space, and you want to express psi as a linear combination of the, once you have a basis, every vector can be expressed as a linear combination of the basis vectors, and if it's a complete basis, you can do so uniquely. Is that clear?
Only thing it is not countable, that's why it is.
Huh.
Since you are talking about spectral measure, I think.
Yes.
No, it is not.
It's not the spectral measure. Spectral measure is connected with the operator and the resolution of the operator in terms of eigenstates. Now, if you are from a mathematics background, let me just say that most mathematicians, including Professor K.R. Parsarthi, who is unfortunately not here, would be very unhappy with my talking about coordinate eigenstates and momentum eigenstates, because you can see here that they are not normalized, right? This is a delta function. They are not norm. But still in physics we deal with them all the time under the assumption that somehow these problems can be taken care of in a more refined mathematically. But since for most of our purposes this is enough, we continue to talk about coordinate, momentum, eigenbasis and so on. Okay. So here what is being done is simply, this is the resolution identity acting on psi, and then I have a resolution of the identity in terms of, for the coordinate basis, so dq q psi, and these are some complex numbers associated with a psi, q taking all values. So we in physics call it the coordinate wave function, or the representation of the vector psi in the coordinate basis. That is the terminology. Huh? Similarly, I do it for momentum. I will get some coefficients of expansion, which are in general complex numbers, one for each p, and we would speak of a momentum representation. All right. So please permit me to use, notions like coordinate eigenstates, momentum eigenstates in the way most of us use them. With the assurance that with a more refined and sophisticated mathematical structure, these questions can be addressed. Now we can construct out of q hat and p hat other operators, and we will quickly look at what their properties are. You could construct, for instance, operators. Let me just look. There's 1 over root 2, things like that. So I can construct operators which I will call complex combinations of q hat and p hat. Q hat and p hat are self-adjoint operators, and I consider these linear combinations of q hat and p hat and ask the question, what are their eigenstates? So what we are doing is looking at defining q hat and p hat are operators which arise naturally. We can construct various operators out of q hat and p hat and look at their properties. We can ask what are their eigenstates, what eigenstates are useful, what kind of properties their eigenfunctions have, and discuss representations of a given vector in various kinds of bases. So, these then obey a hat and a hat dagger obey the commutation relations given here. I have all along put h cross equal to 1. Then we can now ask what are the eigenstates of these operators, and the answer to this question, you can ask this question, what are the eigenstates of this operator? It turns out that the eigenstates can be constructed and they are labeled by a complex number z. There are continuous, the eigenstates of A are labeled by a complex number z, and these are known as coherent states. For reasons that will become clear later on when we discuss quantum optics and connections coherent states. Now, one can discuss the properties. So, we have got so far q, coordinate eigenstates, momentum eigenstates, and the eigenstates of this operator A is referred to as an annihilation operator for reasons that will again, for those who are not from physics background, will become clear later on or in fact in this lecture itself. So, this is what it is now, and we will spend some time in the tutorial doing simple exercises involving these various kinds of states. The third operator that we can consider is, or which is interesting, is this operator A dagger A. You can now ask the question, given the properties of A, what are the eigenstates of this operator, and we call it, give it a name n hat, and it turns out that this has a discrete spectrum. Its eigenvectors are labeled by positive 0, 1, 2, 3 to infinity, and eigenvalues of A are given by n n. So, eigenvalues are numbers which take on values 0, 1, 2, 3 and so on. These set of states, so let me here q is a real number taking values, p is a real number, z takes on values complex, all complex values, n equal to 0, 1, 2, 3. So, these are various operators that you can build from q hat and p hat. We have looked at operators q hat and p hat, and these are so far they are linear, the operators are linear in q and p. The operator A dagger A, for example, is related to up to a constant to q hat squared and p hat squared. So, quadratic operators. Of course, you can go on considering more complicated operators built out of q hat and p hat and investigate their properties if you wish to do so.
But your annihilation operator is not a self-adjoint operator.
Annihilation operator is not a self-adjoint operator, and that is why this set of states that we have written down here will have some special properties. They will not give you a complete basis, but they give you a rather over complete basis, and this we will discuss in the next lecture. But each of these are eigenstates of a self-adjoint operator, and therefore, they give you a resolution of the identity. Every vector in the Hilbert space can be written as a linear combinations in a unique fashion, coefficients. So, so this is the set of another set of operators which are interesting, which are unitary operators on the Hilbert space, and they are the while operators. Please bear with me, I have introducing a lot of operators and the interrelations, but we need them in order to be able to perform any calculation computation, as we will see. So, it is important for you to keep track of their definitions and their properties and what their actions are on various states in order to be able to perform calculations of phase space functions that we will discuss later. So, these are operators of this kind, p q hat, they are exponentials. P here is to be viewed as just a number, a parameter, I p q hat. So, exponential of q hat. Or, all right, these operators, let me call it u p. These are unitary operators on the Hilbert space. Similarly, we can define exponential of the momentum operator. These are also unitary operators on the Hilbert space, equal to V V dagger is equal to 0. Now, what is the action? How much time do I have now? 5 minutes. My time is up otherwise? Oh, good. I am also tired. So, let's just finish with one question. I ask you this question, just to test your quantum mechanics. So, this is the operator given. And this operator acts on eigenstate of the coordinate operator with eigenvalue q naught. And I want you to find out what is the action of this operator on this state. Eh? This is q hat, is a function of q hat. This is an eigenstate, so very simple. It's simply e to the I p q naught q naught. All right, now we change this to p naught. So, this is now a momentum eigenstate, and q hat is an exponential acting on this. I want you to find out, let me just change this. So, q naught u p p naught. What will this be? And these are the kinds of exercises which we will learn how to do in the tutorial this afternoon. I said this is something which one must be comfortable with in order to be able to perform calculations of various kinds in this context. So, I will stop at this stage. In the tutorial this afternoon, I think it will be very good if we become comfortable with the operators that we would be dealing with in the description that appear naturally in the context of quantum phase space description, so that the basic nitty-gritty is all taken care of and one can focus on more interesting things. So, I will stop at this stage. Yes.